Okay, so just a couple examples on solving exponential equations exactly. These can be a bit of a challenge because they rely on a fair amount of algebra, which can be rusty for a lot of us. So I figured I'd walk through a couple that have some interesting components to them, and that might spark some stuff for us. So let's say I've got this equation right here, 200 times 2 to the t over 5 equals 355. So what we're going to want to do, similar to solving linear equations, is isolate the variable using the balance principle. Now, certain moves you're going to do, just like in chess, will result in different board states, right? So what can I do to both sides to result in a better situation? So eventually we're going to use logs, right? Because we're undoing exponents, and logs are the inverse to exponents, just like division is the inverse to multiplication. But if I take the log right now of both sides, I'm going to have this problem over here where I've got, the log of something times something else, and it actually works out to be a little bit more messy. It's still okay to do that, but here's how I'd recommend going about this. It results in a better state. I've got this 200 as like a coefficient times the base equals this real number over here. So what I'm going to do is I'm just going to divide both sides or multiply both sides by 1 over 200. All right, same as dividing by 200 on both sides. What that's going to do is reduce this coefficient to 1. I'll just be left with 2 to the t over 5 here equals 355 over 200. Now this might reduce, but I'm not going to worry about that right now. And I'm going to continue to solve for t. So now I've got a base to a power equals something else. So in order to get access to this power up here, I need to use logs to undo it. So we're going to use logs to undo the exponent, right? Just like division undoes multiplication, logs undo the exponent. So what we do is we take the log of both sides. It could be common log or ln, doesn't matter. If one side equals the other, then the log of one side equals the other. This is the kind of logic we're using here, right? If a equals b, I'm saying these two things are equal, then that means that if I take the log of a, that has to be equal to the log of b because a is the same as b. Okay, so this is like some logical argument that we're using there. So why we do that is because we're using the property of logarithms that allows us to move the exponent to be in the multiplication space. So it becomes now t over 5 times the log of 2 equals the log of 355 over 200. All right, so from here now we can do a little bit more with the properties of logs. So I'm just going to write over here, simplify with log properties. And we just scoot this down. So we're going to simplify this using log properties. This one over here, I have a quotient inside, so I'm going to use that log a over b is equal to log a minus log b. This is the analog for the quotient rule with exponents, right? That we take the difference of the two exponents. So here we get log 355 minus log 200. And then on the left, we still have t over 5 times log of 2. So what I can do is I could do it all in one shot and isolate t, or I could do it in 2 steps, divide both sides by log 2. Log 2 is just a number, right, since we have a real number inside the logarithm. So log 2 is, I don't know it off the top of my head, but it doesn't matter. It's just a real number, and we can approximate it later. And we get log 355 minus log 200 all over log of 2. And then we don't want t over 5 equals something. We want t equals something. So what do? We multiply both sides by 5 over 1. So that these cancel, and we're left with t equals 5 times log 355 minus log 200 all over log of 2. Now, I'd be fine with this. You could break this one up a little bit further, right? Knowing that really log of 200 is the same as log of 2 times 100. And then bust that apart to be log of 2 plus log of 100 because, and why would I do that? Because log of 100 just equals 2. So this would really be log of 2 plus 2. So the more we can break it down, the better approximation we can see for what this value is actually going to be, right? Log of 2 plus 2. Log of 2 is really tiny, so it's, something tiny plus 2. But anyway, this would be fine as is. And you're leaving it in exact form, which means in terms of fractions, logs, square roots, radicals. Basically, you didn't use your calculator to get a decimal approximation. You might use your calculator to do some of this work up here, but we're not coming up with an approximation for the final result. We're using algebra. Okay, so that's what we mean by exact form. So let's do one more, and again, I trust that you're using pause and rewind to hit anything that maybe we went too fast through for you. Okay, and so for this next one, this is going to be a little bit funkier because we've got the variable on both sides. We're being asked to solve for x. And so what we're actually going to do is divide one of these base with the exponents over to the other side. The reason that we're going to do that is if we were to subtract maybe this whole term over to the other side, it's not going to leave us in a good position where we can reduce and get access to the variable which is inside the exponent, right? We want to be able to use logs at the end to bring the exponent down and then solve. So I'm going to use division because by doing that, hopefully we'll have some exponent rules to help us out and simplify some stuff. So it doesn't really matter which direction you go, but I'm going to divide both sides by 2 to the negative x. Okay, so over here, this will cancel. It's good. We'll just be left with 7 on this side. And over here, we're really going to kind of focus in on this piece and this piece. And we've got this 0.4 as like a scalar coefficient to the side. So I've got 1/3 to the 3x. And then when we divide by 2 to the negative x, really this is the same as multiplying by 2 to the x, right? If we remember that property of negative exponents, it means it's the reciprocal, right? So this is a rule that's going to come in handy a lot. And the same thing with if it's in the denominator, this is necessarily true. Okay, so it's a good one to hold on to. So now that we're here, we're closer to what we want, but it still looks a little funky. Something's still a little bit different. So what I see is I could maybe break this apart into being 1/3 to the 3rd power times x. And you might say, why does that help? Well, if I have a product of two exponents, I know that I can use that one property of simplifying exponents and undo it and say this is equal to 1/3 to the 3rd power to the x power, right? Because if I simplified this, I would end up back where I was, right? So this process of unsimplification or breaking apart the Legos is really important here. This takes some experimentation. And you might still be saying, how does this help us? Well, there's another rule, right, which is if you have a to the x times b to the x, this is the same as ab to the x, right? The way we usually use it is to simplify. We'd say if I've got a times b to the x power, this is equal to a to the x power times b to the x power. I'm going the other way on this equal sign and saying I've got this a and this b, and they're both to the x power, and I want to rewrite it like this. 1 over 3 to the third power times 2 all to the x. I've still got this 0.4 out here and the 7 in here, right? So because each of these has a power of x, so I could rewrite it like that. The reason that I've done that hopefully is a little bit more clear. Even though this is kind of funky in here right now, or not simplified, I still have a times b to the x equals something, right? I've got a times b to the x equals something. So that's what I want, because I can use logs to solve this pretty easily. So I'll neaten this up in here. 1/3 to the third power is really 1 over 27, so I've got 2 over 27 on the inside there. And then a 0.4 and a 7. And now I can just solve this like I've solved the others. Divide both sides by 0.4. And so that's like multiplying by, what, 10 over 4? So that's 70 over 4. That might be wrong. Nope, that's right. So, and we can simplify that to be 35 over 2. And over here we've got 2 over 27 to the x, 2 over 27 to the x. And now I can use logs on both sides to solve. So take the log of both sides here to then simplify using x times log of 2 over 27 equals the log of 35 over 2. We'll divide both sides by this quantity here, log 2 over 27. These guys cancel, and you're left with x equals log 35 over 2 over log 2 over 27. Again, we're being asked to solve these exactly, so we're not going to use our calculator here. So the only thing I could really do to break this up any further is go log 35 minus log of 2 over log of 2 minus log of 27. And that's as good as it gets. Don't be tempted to cancel anything here, right? I know we might be looking at these log of 2's. These are not factors, these are terms, so they can't be canceled with each other through division. But that's as good as this one gets. So that had some good review here on the properties of exponents you might need to use in any given moment. This one was a key one, and so was this. And I think I used one more, right? Oh, this one here, which was that a to the b to the c power is equal to a to the bc, and I went this way on that equal sign as well. All right, so that's what I mean when I say going the other direction on equalities. And you'll also notice the other thing that I'm doing here, which is going back over the problem to review what did I use, what did I learn, what did I know. And you should be doing this as well, because that really kind of grooves the pathways in your brain so that when this comes up later, you'll be able to apply it more readily. You won't have to reinvent the wheel every time. So I hope you found that helpful, and that this informs some of your problem solving in 5.1.